These are notes for AP Calculus AB. This is 5.4, and we're going to be working on integration with trig today. So on the side, I've written out the Pythagorean identities to remind you of them, since they will appear every now and then in some problems that we'll be working on. So you can see the three Pythagorean identities on the side. And what we're going to be doing with integration with trig, we're not integrating the 6 trig functions. We're actually working on integrating back to these 6 trig functions. So what we're going to do is start with the derivatives, and then we'll work on some examples on this integration. So in taking the derivative of sine, we're going to get cosine. With the derivative of cosine, negative sine. The derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared. The derivative of secant is secant tangent. And the derivative of cosecant is negative cosecant cotangent. So again, what's going to happen today is working backwards. So we're going to start with things like cosine and negative sine, secant squared, cosecant squared, secant tangent, cosecant cotangent. You may or may not see negatives. You may or may not see other coefficients, but these 6 things are what you're looking out for. These are the things that we'll be working on integrating. If you don't see one of these things, you may have to make a substitution with a Pythagorean identity, or you may have to simplify the trig expression in order to get it into one of these forms. And this is what you're looking for. The better you know these derivatives, the easier the integrals will be. So let's go ahead and start with our first example. Which just has us integrating cosine. So in my list here, the answer of cosine is the derivative of sine. So integrating cosine, we work backwards to sine. So whose derivative is cosine? The derivative of sine is cosine. And of course, we add on c here at the end. So that's going to give us our answer. And we'll move on to number 2. Now integrating sine, so I do have sine in my list, although it is a negative sign. In other words, the derivative of cosine is negative sine. So whose derivative would give me positive sine? Well, that would have to be negative cosine. So that I have a negative 1 coefficient, which I'll multiply with the derivative of cosine. If the derivative of cosine is negative sine, my double negative turns into a positive. And so you can think of it really as just there should be a negative on there. And because there's not, the negative must lie in the answer. So example number 3. One minus cosecant squared. So we either can integrate each piece individually if cosecant squared is one of our options, or we might have to use a Pythagorean identity. Anytime you notice values that are squared, that might come up. So I'm looking first to see if cosecant squared can be integrated on its own, and if it's in my list, which it is. Negative cosecant squared is the derivative of cotangent. So we're going to integrate each piece individually. So integrating 1 with respect to x is going to give us x. Integrating negative cosecant squared, we should get back to positive cotangent. And that's it for each term, so we add c, and we're done. Now remember that you can always verify this just by taking the derivative of your answer. The derivative of x is 1. The derivative of cotangent is negative cosecant squared. The derivative of a constant is 0. All right, so again, we're looking to see if each piece individually can be integrated. So cosine, yes, is in our list. What about cosecant times cotangent? That's also in our list. Although in the list, it has a negative coefficient, and here we have a positive coefficient. So much like example 2, we're going to have to deal with where did the negative go. So we're going to start here with integrating cosine. Integrating cosine gets me back to sine because the derivative of sine is cosine. So this piece becomes sine x. The next piece, I'm looking for whose derivative is positive cosecant cotangent, while the derivative of cosecant is negative cosecant cotangent. So it would make sense that the derivative of negative cosecant would be positive cosecant cotangent. Remember, if the negative is not here, then it must reside on the original function. So it's going to become minus cosecant x. So that's our second piece, and then we'll add c. Again, you can verify this just by taking the derivative. And taking the derivative is really how I'm evaluating it in the first place. I'm thinking about whose derivative gives me cosine, whose derivative gives me cosecant times cotangent, and so on. All right, example 5. So it says integrate 1 plus cotangent squared. So I'm looking to see, well, 1 can be integrated on its own, but what about cotangent squared? Is that one of the values in my list? Cotangent squared is not in my list, so it can't be integrated on its own. So what I want to do here is see if I can use a Pythagorean identity. Since anytime I have something squared, I might be able to use 1. In making a substitution, you might find a new value that is in the list. So 1 plus cotangent squared here is equivalent to cosecant squared. So let's try making that substitution. Okay, and I'm going to make a note here that we did that. And so we're looking to see, is cosecant squared in our list? It is, although negative cosecant squared is in our list. So if there's no negative here, then it must be on the other function. So it's going to end up on our answer. So the answer here is negative cotangent x, and then we'll add c. All right, example number 6. So is secant squared a value that can be integrated on its own? So is it something that's in my list? Yes, it is. It's someone's derivative. So secant squared is the derivative of tangent. You'll see it does have that negative coefficient, which is fine. We're just going to keep it aside and then switch out secant squared with tangent. So integrating 10x first, right? We're just using our power rule really. So we have 10x to the power 2 divided by 2 minus the derivative of what makes secant squared. So I have the derivative of tangent is secant squared. So that takes care of that piece. And then we should just add c here and simplify. So I have 5x squared minus tangent x plus c. Again, you can take the derivative of our answer here to see that we end up with the original integral. All right, problem number 7 starts off this way. Cosine divided by sine squared. And so we learned over the last year or so that with trig functions, fractions, we should be able to simplify as much as possible. So what I'd like to do is split up sine squared into sine times sine. and then just do a little bit of regrouping. So cosine over sine, I can rewrite that as cotangent. What remains is 1 over sine. Now 1 over sine is cosecant. And so I'm looking to see if cotangent times cosecant is one of my answers here in my list. So cotangent times cosecant is one of my values, although it is followed by that negative. So again, with the negative, if it's missing here next to it, then it must be on the other side in my answer. So this will integrate back to negative cosecant plus c. All right, so the last few problems are going to start introducing u substitution along with trig. That u substitution can go several ways. So our first example says sine x times cosine to the 4th x dx. So sine times cosine is never going to be in your list, and cosine to the 4th power is not in our list either. So what happens is we want to think of this as our u substitution rules. Whenever I have high powers, I'm looking to use u substitution here. So that high power for cosine, okay, is what tells me that I'm going to need substitution on this problem. Remember that this is really the quantity of cosine x to the 4th power. So my u substitution, we're going to let u equal cosine. All right, so over here on the side, u is equal to cosine x. We'll take the derivative. We get negative sine x dx. Remember, we're looking for the derivative to be in our leftovers. So my leftovers here, everything outside of my high power is sine x dx. And I almost have that matching. All I need to do is divide the negative over to the other side. And now sine x dx matches my leftovers. So we're going to remove sine x dx and replace it with negative du. So my integral, I have here u to the 4th power. And sine x dx is replaced with negative du. We're going to pull that negative 1 coefficient to the front. We'll leave du over here at the back. And then we're ready to integrate. So I have my negative 1 coefficient. We get u to the 5th over 5 plus c. That's it for integrating. We're just going to substitute cosine back in place of u. So I now have negative cosine to the 5th x over 5 plus c. And that's my answer. On number 9, cotangent times cosecant cubed x dx. All right, so we might consider letting u equal cosecant, similar to how we let u equal cosine in the first problem. If we did that, this becomes u cubed and takes care of all the cosecant terms. So on the side, if I let u equal cosecant, and make this u cubed, then the derivative here of cosecant, so remember the derivative of cosecant is negative cosecant cotangent. Negative cosecant cotangent, which does not match what would be left over, which is only cotangent dx. And we cannot divide cosecant over because you can't mix your x's with your u's in your derivatives. So if I need this to work out, remember that you have 3 cosecants here. So what I'm going to do is I want to keep this going. I'm going to split it up in a way so that I still have a cosecant x outside of my u substitution. The way we do that is just piecing it apart. So we're going to take cosecant, we're going to break it into cosecant x times cosecant squared x. So it could help to rewrite it. You have cotangent times cosecant times cosecant squared dx. So now when I do my u substitution, u is still going to be cosecant, and this is u squared, but the stuff outside, cosecant cotangent dx, will now be able to match. So my leftovers now match what's here in my derivative. So let's just make sure we have our dx here, and then move the negative over so that the right side here matches exactly what's left over in my integral. So again, my leftovers are replaced by that negative du. Cosecant from the cosecant squared is replaced by u. And so my integral is u squared. And the rest, the leftovers here, are replaced by negative du. And so it ends up very similar to problem number 8. So we continue with our integration, negative u cubed over 3 plus c, and substitute cosecant back in place of u. So negative cosecant cubed over 3 plus c. Okay. So imagine taking the derivative of sine 2x. You'd have sine on the outside, 2x on the inside, and so you'd be using chain rule to take the derivative here. Well, that means we need to use u substitution in order to integrate. This time, though, the u substitution applies to the stuff inside of sine. So how do we know when we need u substitution? One thing was those higher powers or a kind of radical, a square root, a cube root, and so on. But grouping symbols were a part of that. A trig function can act as grouping symbols, or that is 2x is inside of sine. We're just missing our set of parentheses here. So we're going to let u equal 2x in this problem. So on the side, if u is equal to 2x, then du is 2 dx. So we're looking for this to match what's outside. Here's where you have to be careful. In a case where you're substituting for what's inside of the trig function, we're not actually going to replace the trig function itself. We only care about replacing anything outside of the trig function, and the only thing outside of it is the dx. So in order to make that match, we'll divide by 2. 1/2 du is equal to dx, which now matches my leftovers. So we're going to go back in and make these substitutions. So this turns into sine u. In the same way that we leave the exponent when we do our u substitution typically, so u squared or u cubed, in this problem, the sine is the part that stays in the problem. So this is sine u. And then we replace dx with 1/2 du. I'm going to pull that 1/2. It's my coefficient all the way to the front. We're always going to leave du at the back. And from here, we can do our integration. We're going to keep our coefficient 1/2. And then we're just worried about integrating sine. So remember to check your list. Sine is a value that's in our list. Okay, to get sine, well, we'd have to take the derivative of cosine. Well, the derivative of cosine should give me negative sine. And right now, in number 10, I have positive sine, which means I must be taking the derivative of negative cosine. So this would be negative cosine u plus c. So just a little bit here to clean up. We're going to pull that negative out front with the 1/2. And we'll replace u with 2x plus c. And so you can verify this. So integrating sine gets you back to cosine. What's inside stays inside. But when you're taking derivatives with chain rule, remember that the derivative of 2x would be to multiply by 2. When integrating is the inverse operation. So instead of multiplying by 2 in the end, you divide out by 2. And that's a quick way to see that what you're doing is coming out correctly with your u substitution. So that ends our notes for objective 4.